$20,000. That's how much I estimate this one mistake we've made when designing this board has cost us. And now that we've resolved it, I'm not even mad. I'm just happy it's over and we can now move on. Let's talk about it. If you're new here, hi, my name is Tomasz, and together with my co-founder and friend Aljaž, we're building, well, what we think a perfect 10 gigabit router should look like. And I don't mean that visually, well, we do think it should also look great, but apart from that, we're using high quality components in its design. We plan for it to come with plenty of documentation, stellar support, but above all, to afford you the freedom of choice. You wanna run bare Linux? You'll be able to do it. OpenWRT? Check. ViOS? Check. We're even talking with some experts on the matter to hopefully port OpenSense to it, but the point being is, while we do want to develop our own solution based on vector packet processing long term, and go ahead and click that subscribe button for that because I will ask for plenty of feedback once we get there. What I value the most in the devices that I own is that they allow me to use them in whatever way I prefer to use them, not how their developers want, or in most cases, force me to use them. Let's start with the good news, and that's the fact that we finally resolved our DDR issues, or should I say issue. Because there was this one tiny minuscule detail that not only all of us missed, but even the external help that we hired eventually did the first time they reviewed our schematics and layout. Now, before I reveal what this issue was all along, let me explain how a normal bring-up process looks like with NXP CPUs, one of which we use on our board, and I imagine other vendors don't differ from this process much, if at all. So, first, you need to sort out your firmware, or more specifically, a piece of code that's called BL2 or bootloader 2. This is the first piece of code that is external to the CPU, meaning it's stored in a NOR flash or on an eMMC chip, as opposed to BL1 microcode that is normally stored in what's called an OC RAM or on-chip RAM, and that chip in this context is the CPU itself. The primary purpose of this BL2 firmware is to configure the memory controller, and once it's done with that, to copy the BL3 firmware that's normally stored on the same chip as BL2 into now running memory, and finally execute this BL3, the main part of which is the first interactive piece of code that you probably heard of before, U-boot. And yes, that does mean that in order for U-boot to run at all, you need, well, working memory. Which almost looks like a Kids are screaming outside. Which almost looks like a chicken and egg problem, but not quite. You see, the QCVS, the tool that NXP provides to configure the DDR controller, you need a system that is somewhat up and running so that it can discover the best settings, and the keyword here is somewhat. And how you get to this somewhat is not RTFM, but RTFDS, or read the fucking datasheet. There's only one file in BL2 that's important here, and unsurprisingly, it's named ddr_init.c. In this file, you have to configure CPU memory controller registers, and the values you need to enter can be found in the datasheet and may differ quite substantially depending on which speed bin you choose to implement. Although our controller supports speeds up to 2100 megatransfers per second, we initially decided to go with 1600 megatransfers per second, which allows for a little less strict timings, you know, to have some wiggle room, and here's how the final file looks like. I won't go into details here, just know that each of these lines corresponds to a certain register, the documentation for which can be found in the CPU datasheet, and the values for which can be found in the memory datasheet. And here's where the somewhat working memory I mentioned earlier comes into play. For us to be able to run what is called a DDR centering, more on that soon, we needed to build a BL2 that was good enough for the memory controller to not report any major issues when booting up. Except it did report a major issue, but to our surprise, booted up anyway. In fact, it booted up so reliably, we were able to boot the whole system straight into Linux. And the issue I'm talking about? Well, the issue is called an ACE and was the first issue we've had with our prototypes that literally made me lose sleep over it. ACE stands for Automatic Calibration Error, which means that the memory chips weren't able to properly calibrate themselves, which is part of a training routine that the DDR controller goes through on every boot. Now, to understand why this bit is important, let's look at what the process looks like if this bit is not set, meaning we have 100% perfectly configured and working DDR. In that case, what you do on an empty board is you first flash the NOR chip with a somewhat accurate BL2, which, as we already established, configured the DDR controller. But because there's no BL3/U boot on the board at that point, it errors out because it cannot find it. But despite that error, we do have a running board with a working DDR at that point, to which we can connect from our PC using the JTAG connector and run what is called a DDR centering test. But to understand what this test does, we'll dig even deeper into how memories work, and I'll try to keep it as simple as possible. You see, there are several types of signals that travel between the CPU and the RAM chips, and the two most important types in the context of centering are the data signals and the clock signal. Data signals are quite simple conceptually. We have 5 chips, and each of those is directly connected to the CPU with 16 traces, except for the ECC chip, which uses only 8. This means that each RAM die has 16 data pins, and because the CPU has 72 of the matching pins, this means we can connect up to 4 RAM chips for a total of 64-bit wide bus, or, because we're running ECC in our case, 72-bit wide bus. Since routing all these signals can become quite a challenge, DDR standard allows for something called bit swizzling. In a nutshell, because memory dies come in all sorts of sizes and configurations, bit swizzling basically allows hardware designers to connect bits within the same nibble to the CPU however which way they want. A nibble, in case you didn't know, is the term we use to describe a group of 4 bits. Half a byte is a nibble. To not overcomplicate things, think of bit swizzling like this. You have 16 data lines that connect the CPU to the first DDR chip, for example. Now group all of them into 4 nibbles, so bits 0 to 3 are a nibble, 4 to 7 are a nibble, and so on. What the standard allows you to do then is to connect the pins within each nibble however it makes the most sense and is the easiest from a hardware design perspective to the corresponding nibble on the CPU. This means that each nibble pair essentially has 24 possible ways to connect the memory die to the CPU. So 96 possible combinations per each of the 4 memory chips we have on board, and 48 combinations for ECC because it only uses an 8-bit connection. Now, unlike the data signals that are used for, well, data to travel in both directions, clock signal only gets generated by the CPU and gets sent out to all the memory chips at the same time. And by far the most popular way of routing the clock signal is known as a flyby topology, which essentially looks like this. You have your data signals that directly connect the RAM chips to the CPU, and then you have your clock signal that comes out of the CPU and then goes to the first chip, but instead of stopping there, it then goes on to the next and the next and the next until it finally connects all the chips and then ends its journey in what is called a termination register. But this approach has a problem, and that problem is that the clock signal doesn't arrive at each chip at the same time, which means that if we launch both signals at the same time, the clock and the data will arrive to the chips at different times, which is a big no-no. In our case, the difference between the clock signal and the data to the first chip is only 32 millimeters, while the difference between the clock signal and the data signal to the last chip is a whopping 92 millimeters. In a nutshell, DDR centering is a procedure in which you measure how much delay you need to apply when reading or writing to each individual memory die to make sure that the data arrives almost at the exact same time as the clock signal does. I'm saying almost here because there is some wiggle room in both directions, but as the name suggests, the center is where we want to be because this gives us the highest stability and best resilience towards power spikes, temperature drifts, and electromagnetic interference. And this is how DDR centering works in NXP's tool called CodeWarrior. See all those blinking cells in the table? Each column represents a byte lane, meaning 8 individual traces or bits to the memory die, and the software basically moves this delay up and down until it cannot write to the memory because the delay is either too long or too short, and then recommends the middle or the center to be the best option. What's going on here is the controller starts the clock, waits a little bit because the clock signal needs a little bit more to arrive at the memory chip, then sends the data to the chip it's testing. Then it reads that data back, and if it matches to what it sent out, we have a successful transaction, which is what all these green cells here indicate. If it doesn't succeed, on the other hand, it knows that the delay was either too long or too short, so it moves it back or forward a step and tries again. But there is a catch to all this. You see, before centering can be done, the DDR controller's error registers need to be empty. Because if they're not, this whole thing won't even start, which makes sense really. You rely on the DDR reporting an error when the delay is too long or too short, so testing doesn't even make sense if there's always an error, right? And in our case, there was always an error. Remember the automatic calibration error I mentioned earlier? Well, no matter what we tried, and trust me, we tried a lot, as in we tried probably a gazillion different settings and combinations over the course of past 2 months, this error simply wouldn't go away, which meant we were unable to complete the centering successfully. But the part that confused us the most was the fact that we were able to read and write to all regions of the memory successfully, and on top of that we were not only able to boot into Linux, but even run some basic stress tests, which granted would fail eventually because the centering hasn't been done properly, right? Well, eventually we kinda gave up and decided we need a 5th set of eyes to maybe bring some fresh perspective. So I asked around and found somebody who's done this for like 20 years now, and even that person only found the issue on their 3rd attempt. And you know what it was? Remember bit swizzling we spoke about a minute ago? Well, you can swap bits within a nibble on purpose or by accident. I'll give you one try to guess which one of the two we're guilty of. Basically, when we were routing the traces on the PCB, we mistakenly swapped a couple of traces, which, as I said, is perfectly fine and within standards, and honestly an easy mistake to do given the complexity of routing memories. But when you do that, you still need to tell the controller how bit swizzling has been done so that it can configure itself properly. But because we thought we routed traces without any bit swizzling, we misconfigured the controller, which in turn resulted in the automatic calibration error. Obviously, those couple of bits being swapped wasn't done on purpose. Think of it as a sort of a copy-paste error, and with 64 data lines in total, or 72 if you count ECC, it became somewhat of a forest for the trees kind of situation. Situation that at some point I got so frustrated by that I said, fuck it, let's bring someone impartial to look at the thing, and sure enough, that decision turned out to be the correct one, because in a couple of days they came back and said, guys, here's your problem. 2 months of almost full time of my work down the drain. Now, of course, once we configured the controller with those couple of bits swapped, everything started to work correctly. The centering passed, all of our eye diagrams looked perfect, and all the overnight tests that I've ran over the course of the past week passed with 0 issues. Of course, this is a bit of a trust me bro approach, and for now it's perfectly fine, but for the first batch we will of course hire a lab that will let us run these in a proper, more scientific, numbers only kind of way to make sure that our DDR configuration is nothing short of perfect. Now, before we move on, a question that's worth answering is, why did it work then? As in, why could we boot into Linux despite the fact that we've had a couple of bits swapped in our layout? Well, because RAM is a fairly stupid device. Think of each chip as a rack of drawers. The rack doesn't really care which drawers you put stuff in, as in organizationally, as long as you put stuff labeled A into drawer for the stuff labeled B. And if you do it consistently, 100% of the time, then you'll never get confused or have things corrupted, right? But when the CPU is booting up, and keep in mind this is my assumption at this point because it's not actually documented anywhere, I suspect the controller at that point does care about the organization of the drawers in the rack or how the bits are wired to the CPU. And in case it finds anything, it sets this calibration error bit with zero explanation as to where the issue might be. And as to why this behavior is not documented anywhere, ask NXP. We certainly did, multiple times in fact. And multiple times we were offered their $200 per hour support package. It is what it is. At this point, I'm just happy it's over and we pretty much solved 100% of all the issues we encountered on the first revision of prototypes, not just DDR, and can now finally order the second revision, which will likely happen in a week or so. This episode is brought to you by PCBWay. I've been working with them on my custom keyboard project and I was super impressed with their speed, quality and price, so I'm more than happy to recommend them to anyone who needs any kind of PCB manufacturing done, whether it's just for a couple of prototypes or if you need a larger production run. Link to their website, of course, down in the description. Back to the video. Okay, now to the bad news, or more of a rant, I guess. You see, over the past couple of months, I've been rejected over and over and over by the investors, and honestly, it's been insanely frustrating. And I'll tell you why. When you're working on a pitch, you obviously have to discuss many possible angles, or to put it differently, you have a number of check boxes you need to tick off. And if you look online for a perfect tutorial or even a blueprint, most of them will probably have 95% of things in common. As in who the founders are, what the problem is that they're solving, what the market size is like, what kind of solution they have, how much, if anything, they raised so far, what the risks are, and so on and so forth. The most important question, I would argue, is one of a growth potential, right? Because that's what investors ultimately want. They want to put X amount of money into a startup and hopefully see it explode in X years into the future. That growth potential, of course, needs to be there in terms of a number, but what is even more important is some kind of proof that you can actually get there. And I was under the impression that with almost 1,000 units pre-sold in just over 3 months, that would be, proof enough for the investors that we can see some early market traction. I mean, we were able to raise almost $100,000 from our prospective customers, so that's proof enough, right? Well, I certainly thought so, and yet every single email I've sent so far, and all the emails my connections have sent, the one reply we always get is, we do not invest in hardware. I mean, I get it, right? A piece of hardware can never become viral. There are exceptions to this, but for the most part, we cannot and will not become a billion-dollar company overnight. Now, don't get me wrong, every business owner dreams of becoming wildly successful at some point, but we're not going to get there in a matter of months, right? I even asked our angel investors from whom we raised almost 400k at this point. I said, listen guys, I have built and sold a company from scratch before I started this one, and I'm talking a multi-million-dollar company here. So I'm fairly confident I can pull this off the second time, right? And Talyash, my co-founder, used to work for ASML, and you don't get invited to work for them if you're not a world-class engineer. Which means that between the two of us and the rest of the team that's helping us with the project, we share enough knowledge, skill, and experience to not make any major mistakes that would be detrimental to the success of the company. But just having the right people is obviously not enough. There has to be a market for the product they're making, which means that potential customers need to validate this problem by either providing enough feedback or ideally by pre-ordering, because it's often all unicorns and rainbows until people have to actually pay for something, right? And well, we've achieved that as well. So almost 1,000 of you agree with us that a product like ours does indeed have a place on the market. And some of you have even gone as far as to pre-order more than one unit, which I honestly can't thank you enough for doing so. And by the way, since we're talking about money and pre-orders, just for transparency's sake, I think it's worth pointing out that we have not and do not intend to touch any of those deposits at all until the units are ready to ship. This is your money and I treat it with utmost respect, which is why I created a completely separate account for it and we're not touching it, period. Anyway, back to the fundraising. The fact of the matter is, I get it. Investors prefer investing into software because it's a safer bet. No matter how great our product is, it'll never go viral in a traditional sense of the word because, to produce a certain amount of boards, we first have to order all the components, then we have to order the PCBs, and then we have to book the pick and place lines. And guess what? There's a queue and a process for all of these steps, most of which can take weeks, if not months. And in case we mess up the hardware in whatever way, well, there's no easy bug fix we can just push to the cloud, right? So yes, I do believe we have a solid founding team, a product that people are willing to pay for and thus fill a gap in the market, and even a bunch of angel investors that have invested almost $400,000 into this project. So why is it that we're being rejected by all the investment funds? Well, truth be told, I don't know. What I do know is that this is a numbers game and we just have to keep trying, because at the end of the day, you only need one person with enough say on the matter and of course enough money at their disposal to take a chance on you that will say, let's do this. And the bigger the number of investors we pitch to, the higher the chances of finding that one right person. But I'm not gonna lie, it's stressful. In fact, it's stressful as fuck because I do consider myself a maker first and foremost, and having to focus on the money side of things instead of, well, engineering challenges, well, let's just say it isn't my first choice as to how I would like to spend my time. But if that is what it takes, well, then I'll happily focus on this for however long it is necessary. And I did get a couple of you actually reach out saying you'd invest anywhere between 50 and 100K. But, and I don't want to sound ungrateful here, 100K is just not enough at this point. And let me explain why. Our current burn rate, which is what our monthly expenses amount to, is roughly $20,000 to $25,000. And we do have this part covered by our existing investors. What we don't have covered, and is the main reason for us fundraising, is being able to actually produce the development kits that all of you have pre-ordered. You see, to manufacture all 1,000 pre-ordered units, we'd need roughly 400K, 100,000 of which we already have from the pre-orders, which means we'd need at least 300,000 more. And that doesn't count any salaries, licenses, external contractors, anything really, just the cost of manufacturing. What I'm saying is, while we certainly want to raise, sufficient amount of funds to bring us to the Founders Edition sometime early next year, the minimum we're looking at this point to keep the company running and produce the first 1,000 development kits is around $500,000. We'll get there, I have no doubt in my mind, but I wanted to share my thoughts with you because journeys like ours are not all rainbows and unicorns all the time, and I figured, you know what, if I celebrate the highs, why not also share the lows to give you the full picture of how things look, right? Now, before we wrap this part up, I need to ask a favor, because whenever I post any kind of problems that we're facing, I get a ton of emails from a lot of you asking how you can help, and this actually always surprises me and I'm immeasurably grateful for. So here's how you can help. If you know someone that works at or runs an investment fund, work at one yourself, or even know someone in a larger corporation that takes a chance on small startups like ours, get in touch with them and tell them you follow someone on YouTube that is working on a router project that you decided to pre-order because you like our approach so much. And don't worry, if you're bad at pitching, I've actually gone and prepared a piece of text that I'll leave in the description of the video, and all you have to do is copy and paste it into your email client and you're good to go. And second, and this is somewhat of an exercise for myself as well, down in the comments, please take a minute and write in just a sentence or two what you think makes us different or unique compared to the competition. What do you think we bring to the table that others do not? I mean, I do think I know what it is, but think of this as me double checking if you all perceive us in the same way that we perceive ourselves. And because I know from experience that plenty of you will do what I'm asking, let me thank you in advance. Seriously, you're the best audience one could ask for. Again, thank you. Okay, time to wrap this video up with a piece of good news. Very good news, in fact. Our router passed what is called an EMI indication test, but to understand which ones in particular, have a look at this chart. At the top, we have EMC, or electromagnetic compatibility. As per Wikipedia, EMC is the ability of electrical equipment and systems to function acceptably in their electromagnetic environment. Acceptably in this context means that they don't pose any health risks or electromagnetic disturbance to either humans or other electronic devices in its vicinity. EMC testing is furthermore divided into emission testing, which we're discussing in this video, and susceptibility testing, which we haven't done yet, but we'll talk more about once we get there. Worth Electronic, the company that provides quite a number of electrical components for our boards, recently invited us to pay a visit to their newly set up EMC indicative testing facility in Eindhoven, Netherlands. And best of all, as their customer, we were offered a full day of testing completely free of charge.
As you can see, we are now in the Worth Electronic EMI debugging lab from the Benelux. So what we have are a couple of test methods that we are applying for our customers to give them an idea how their devices behave looking at EMC. Maybe from a starting point, we can enter our semi-anechoic chamber, or I need to say full anechoic chamber. So what we are doing here is giving an indication about the emissions, the radiated emissions of a customer. So we have a biconical antenna and also a turntable, a manual turntable, where we can turn the application and see from every angle what the emissions are from those from that application. So it's an automotive size gauge, so it's not a fully compliant 3 meters, but it's around 2 meters, 2 meters 50, and from there we can give them an ID, or customers an ID, how big their emissions are looking at versus the limit. So all the red flags about emissions, I would say for 90% we can see. So we have made it a full anechoic chamber, so it's 360 made, so absorbs 360. So that's also an advantage for us, that we don't have to change the antenna height. So sometimes in EMC labs you see the metal floor. So this is also a metal floor beneath the vinyl, but you will see that you then also need to change the antenna height up to 4 meters sometimes. So that's why we have chosen for this setup.
While testing the radiated emissions in the anechoic chamber was definitely the focal point of the day, we were also offered to do conductive emission testing, which took place just outside the chamber on what is called the ground reference plane. You see, electronic devices don't just emit electromagnetic waves when in operation, they also disturb the mains power network when they are connected to it. Think of it like a huge town water reservoir, and the more people that open their faucet at the exact same time, the lower the pressure each individual household gets. But what's more important, it's the constant changing of the pressure that can pose a problem to certain devices that rely on it being constant throughout time. And the same logic applies when it comes to electronic devices. So what we did for this conductive emissions test was we connected our device to a specialized Rhodes-Schwartz two-line V network, as it is called, powered it up, and failed. As in, the test failed because it showed that our chosen power supply exceeded the allowed threshold at some frequencies. Nothing major, but certainly wouldn't pass a real certification test. Luckily, one of our team members did happen to have a Lenovo USB-C power supply with them, so we decided to use it instead. And guess what? We passed with flying colors, which means it's not our boards that's the problem in the chain, but the power supply, and that is good news. And yes, we did reach out to the manufacturer of the power supply and are talking to them as on a possible solution, but alternatively, we can always choose a different one. In any case, I'll report here on this channel once we do either, so find a solution or an alternative power supply unit. Once we were done running the conductive emission tests, it was time for the grand finale, the anechoic chamber. We decided to conduct all the subsequent tests with the Lenovo PSU simply because we knew it was proven to be within specifications and will not be the cause of any issues because we wanted to focus on our board and not the power supply, right? And good news, we passed. Each and every test we performed was within limits, which means that if this was a real compliance test, we'd receive the certification.
I have seen issues with customers at higher frequencies with a lot of more noise, but this is quite fine.
We even overdid it, in a manner of speaking. We tried a number of possible orientations. We tested it with aluminum enclosure, with polycarbonate development kit enclosure, and even with the bare naked PCB. And each of those tests, to my immeasurable happiness, turned out positive. As in, we comply with what the European standards for electronic devices dictate for a class of device like ours. Now, keep in mind we don't plan to officially certify our development kits because A, it takes much more than a day to do it officially, B, it costs way more than just a plane ticket to the Netherlands, and C, which is what I'd argue is also the most important argument, the development kit is not a final version of the PCB. And if you make any changes to the PCB, and I do mean any, then you have to recertify it all over again, even if it's just a value of a single resistor. Regardless, I'm quite happy that our development kits comply with EU standards, which both means that even if they won't be officially certified, we can all sleep a little better knowing that they're safe to use and also that we don't need to fix anything on our boards to become compliant. Which honestly is a huge deal because it's quite a substantial amount of work on power supplies in particular that needs to be done if a board turns out to be non-compliant. Okay, because you've been such a good sport and watched this video all the way through, here's a little gift from me. These are the renders of what we consider are pretty much final enclosures of the development kit. There's a couple of details I don't want to talk about it in this video because it's already long enough as it is, but make sure to hit that subscribe button because we'll go in much more details about it in the next video. Tomasz from Slovenia, signing out.